So in this 32nd lecture, the topic that I'll discuss is the current components of semiconductor or current components in a semiconductor. What are the current components or what type of currents are there? Now in semiconductor, when I talk about semiconductor, the current, there are two types of currents in semiconductor. First is called the drift current. It is divided into two parts. One is called the drift current and the other is called the diffusion current. There are two types of currents. I'll discuss them one by one. Diffusion current, and rather we'll focus not on current but we'll focus on current density, which is represented by J. This I will discuss the current density, whether drift current density or diffusion current density. This current density is represented by the letter J, so by the alphabet J, and this J is nothing, it is the current flowing per unit area. That is called the current density. So we'll discuss the drift current density and diffusion current density. So it is in two parts. One is, first I called it a drift current, that is drift. If I classify this, it is drift current, and second is called the diffusion current. Two types of currents, drift current and diffusion current. So first I'll come to drift current density. What do you mean by this drift current, or what is the drift current density? So first let's discuss the drift current. I have already discussed with you drift current little bit. What this drift current is actually, as I told you, that suppose you have suppose this is a conductor here. We'll discuss about we'll generalize it for a semiconductor, but suppose I say that this is a conductor here of length L, and suppose I say that the cross-sectional area of this is A, and if a potential of V volts is applied, or an electric field of V by L is applied across this, naturally, as I told you, that on the application of this voltage, the electrons or the charge carriers, they drift in a particular direction along the direction of this electric field E, and this E is nothing, it is equal to V by L, and because of the drift of these electrons or these charge carriers, a current will flow, that is called drift current. I told you that the charge flowing through this, charge crossing the conductor, charge crossing the conductor, this conductor, I suppose I say it is equal to Q, is equal to N into E into, if you remember, L into A. N is the number of charge per unit volume. E is the charge on one electron. So per unit volume, total charge is this. In this much volume, volume is A into L. So charge flowing this. Now I say charge flowing per unit time. Suppose I say what is the charge flowing per, okay, I'll say current, that is charge per unit time flowing through this conductor. That is, I can say it is the current Q upon T. Q upon T, it is nothing, this is the current I, and I call this a drift current as I drift. It is the drift current, and this is equal to Q upon T. So I can say it is equal to N into E into A into L by T. And if you see that this is the length which this charge has to cover from this point to this point, it travels this distance in time t. So this L upon T is nothing, it is the drift velocity. I have discussed this point prior to this also. This L upon T is the drift velocity Vd. So I can say that this current I, this drift current I is equal to, it is equal to N into E into A into drift velocity Vd, and this I upon A, this I upon A, which I call as current density. This J is current density. This J is nothing, it is the current density. Current density, that this A, current per unit area. J is equal to I upon A. I can say it is equal to N into E, and this VD, can I write this VD is equal to mu into E? I replace this VD. What I am doing, I am replacing this drift velocity by mu E. This is what I have done here. Drift velocity by mu E. And if you see that this mu NE, if you look at this factor, this mu NE is nothing, it is equal to the conductivity sigma. So from here I can say that the drift current density, it is drift current, and J is the drift current density, is equal to sigma E in general for any conductor. Now when I talk about the semiconductor, in semiconductor you will have electrons as well as holes. So I can say that for semiconductor, this current density, I can say it is, or I can say this is the drift current density. J drift I am writing is the drift current density is nothing, it is equal to the drift current due to electrons. J drift, J and drift means N means electrons. This is representing negative electrons. So it is the drift current due to electrons plus the J P, that is the drift current due to holes. I hope that this is clear to you. So drift current is because of the drift of the electrons due by the applied electric field here, and this drift current, again I can apply this, you can expand, I'll expand this later on. This is equal to this much. So I hope that this point is clear to you. Next current that I'll discuss is the diffusion current. What do you mean by the diffusion current? I hope drift current is clear to you. Let's come to another point that is called the diffusion current or diffusion current density. I'll discuss this simply by J diffusion. That is how I'll differentiate between the drift current and diffusion current. I write here J drift means this is the current drift current density, and when I write J diffusion, this is the diffusion current density. Now what do you mean by diffusion current? First of all, suppose you have a semiconductor here, or it can be a conductor also. If you have a conductor here and there are electrons or holes as well as holes also, let's talk about, suppose these are the electrons in this semiconductor. In this semiconductor, these are the electrons, and the concentration is like this. That is, you have large number of electrons in this area and a comparatively smaller number of electrons in this area, or the current density is more here as compared to this. So naturally what happens, that these electrons, they diffuse from higher concentration to lower concentration. These charges, they diffuse from higher concentration to lower concentration till equilibrium is maintained, of course. And of course, whenever there is a flow of charge, there is a current. So this diffusion current, this process of flow of anything, it can be any quantity, from higher concentration to lower concentration is called diffusion. And since it is a flow of charge means current. So due to the movement of this, due to the flow of this, due to the non-uniform charge gradient, this is called the diffusion current. So I hope that this diffusion current is clear to you. Now suppose I say that I assume a small strip here. Suppose I say that I assume a small strip here, and the distance of this is dx. It is x and it is x plus delta x. It's a small distance and the charge is flowing here. So for this I can say diffusion current, that is Jn, means due to electrons, Jn diffusion. I write this as diffusion. That is a diffusion current due to electrons or due to the flow of electrons from higher concentration to lower concentration. It is directly proportional to. It is directly proportional to, if I say that small n, suppose I say that small n is the electron concentration, is the electron concentration, and suppose I say that small dn is the concentration of electrons or the change in electrons in this small distance dx, so it is directly proportional to dn upon dx. That is called the charge gradient in this direction. And of course, if the charge on one electron is E, so it is equal to this much. So from here I can say that the value of Jn, that is the current density, diffusion current density due to electrons, is equal to, I'll have to remove the sign of proportionality from here, and it is equal to dn into charge on one electron is E and dn upon dx. I hope that this is clear to you. Similarly, I can say that the diffusion current density due to holes, Jp, I represent this by P, and I write here diffusion. That is the diffusion current due to holes. Of course, this will be proportional to minus of, if electrons are flowing in this direction, apparently the holes will flow in this direction. And suppose I say that P is the hole's concentration. P is hole concentration. Hole concentration. And suppose again I assume that this is a strip here. This is a strip here. These are the holes. Large concentration. Then here you have lower concentration. Again I assume that if this distance is dx, the small distance is dx, and the amount of charge, change in charge in this small region dx is dp, where p is the whole concentration. So it is directly proportional to dp upon dx and E dp upon dx, where E is the charge of an electron. I hope this is clear to you. If electrons are flowing in this direction, apparently the holes will flow in this direction. So it is minus of this sign in relation to this. It is minus of this. So from here I can say that this Jp diffusion, I remove this sign of proportionality, is equal to minus of dp into E into dp upon dx, where this dn is called the diffusion constant of electrons. This is called the diffusion constant for electrons. And this dp, this dp, this d in suffix p, this is called the diffusion constant for holes. This is called the diffusion constant for holes. Now let's talk about the total current. When I talk about the total current, so this is the drift current and this is diffusion current. Now I say another topic that we'll discuss here, that is the total current in semiconductor. Total current density, not only current, I'll say current density in semiconductor. What will be the value of total current density if I talk about? Now if I said that the total current density is J, suppose I say total current density is J, of course this will be equal to total current is the sum of drift current plus the diffusion current. It is the sum of drift current and diffusion current. Now what is the drift current and diffusion current? Let's see. I am rewriting this, that the total current density J. I said that the total current density, which is equal to J, is equal to J drift plus J diffusion. Again, when I talk about this drift current is due to electrons as well as due to holes. So I can say that this J drift is nothing, it is equal to J N drift plus J P drift plus JP drift. I hope this is clear to you. That is a drift current due to electrons and drift current due to holes. And when I talk about diffusion, similarly you will have this diffusion current due to electrons. I name this as Jn diffusion plus Jp diffusion. I hope that this is clear to you. That is total current is drift current plus diffusion current. Drift current will have two parts: drift current due to electrons and drift current due to holes. Similarly, diffusion current will have diffusion current due to electrons and diffusion current due to holes. Due to electrons, I am representing by suffix in N, and holes I am representing by suffix in P. Now J drift, look at this J. We have discussed that this J is equal, this drift current density is equal to sigma E. This drift current density is sigma E. So due to electrons, I can say that this is equal to, I write this as sigma N into E plus this factor will be sigma P into E. I hope that this is clear to you. And look at this term. Plus, I write this as we have just derived that this is equal to E into dN and charge gradient dN upon dx. This factor was minus. I am writing this Jn E dN upon dx, and this is minus E dP upon dx. Minus E dP constant into dP upon dx, charge gradient. I hope that this is clear to you. Now this J, sigma is equal to mu Ne. We derived that sigma is equal to mu Ne. If you remember, sigma is equal to mu into N into E, or mu into charge density into electronic charge. Which charge we are talking about? Now when I talk about electrons, this will be equal to, if you see, this factor is equal to, sigma is equal to mu N, because it is electrons, N into E into small e, mu Ne, and of course this E is already there, plus for holes this will be mu P into E, and this capital is already there. Sigma is equal to mu Ne into E. Here it will be mu Ne, in spite of mu it is mu P, in spite of N this is P and En, plus the same factor. I rewrite this again, E into dN upon dx minus E dP into dP upon dx, electron current and hole current. Now from here I can take something common. I can say it is equal to, or you can, alright, let's write it here, is equal to, it is equal to E and E common. So it is I can write here N mu N plus P mu P, this factor E into E, plus, if you see what is common, E is common, so dN into dN upon dx, sorry, minus dP upon dx, and all I have done is taken E common from here, and overall I can take this E common from this. So this is the torus current density. Now one more thing, if you observe, in case of diffusion current, drift current, the constant is this mu. And in case of diffusion current, the constant is this dN or dP. Here is mu n or mu p. Now there is a relationship that is called Einstein relationship. Einstein's relationship. This Einstein relationship says that this dN upon mu n is equal to dP upon mu p. This is equal to a constant. It is a constant, and it says that this is equal to kT upon q. A very important relationship. That is called the Einstein relationship. dN upon mu n is equal to dP upon mu p is equal to kT upon q, where this k is the Boltzmann constant, where k is Boltzmann constant, and I think that you know the value of this Boltzmann constant is I think 1.38 into 10 to the power, I think it is minus 23 or minus 28. I wanted to cross check it. Minus 23 joule per coulomb. Please check it. This T is the temperature in Kelvin. Temperature in Kelvin, and Q of course is the electronic charge. Charge of electron. And if I substitute this here, that is, you can say dN upon mu n is equal to dP upon mu p is equal to, if I substitute this is equal to this much, if I substitute this k is equal to this much, and q is equal to 1.6 10 to the power minus 19, this is 1.6 into 10 to the power minus 19 coulomb. If I substitute this value this much, and this value this is equal to this much, this comes out to be approximately equal to this kT upon q. This will automatically be equal to T upon 11,600 approximately, although this is 598 something, but this comes out to be this much. So this is called the Einstein relationship, and this is the total current, as I have discussed here in this article. The total current once again is the drift current and diffusion current. Drift current is due to the applied electric field, and this diffusion current is due to this potential gradient here, or charge gradient, potential gradient, or due to the non-uniformity of the charge. When you have higher concentration on one side and low concentration on one side, so the flow of charge from higher concentration to lower concentration, that is called diffusion current. So total current is drift current plus diffusion current from here, and this is the Einstein relationship, which relates the constant in diffusion currents and the constant in this drift current as kT upon q. So I'll stop it here for the time being. Thank you.